Okay, I'm going to go through this unit test, practice test for Unit 10. And we'll start off here. It says, okay, now notice we do have a couple of formulas here that we might need somewhere along the way. This is for the root mean square velocity, and this is for Graham's law. Okay, a crystalline solid displays the following properties. It has a melting point of 775, that's pretty high, does not conduct electricity as a solid, and it's soluble in water. Okay, so which of the following could it be? Okay, well, the soluble in water, that definitely knocks off the diamond, that knocks off zinc, and that knocks off P4O10. Okay, so right there, it has to be an ionic compound, okay, because it is soluble in water. That pretty much makes it the answer right there. Number 2, okay, boron is introduced into a crystal of silicon, which allows the silicon to significantly increase its electrical conductivity. Which of the following explains its results? Okay, remember, silicon is something that has 4 valence electrons, where boron is one that only has 3 valence electrons. So if we have this boron in with those, it's going to leave little holes, okay, in the crystal structure that can pass back and forth, and that's going to make it turn to a p-type semiconductor. So let's see if there's an answer like that. Boron has a sea of electrons. No, boron doesn't, because a sea of electrons means a metal, and boron's a nonmetal. Boron has fewer valence electrons than silicon, which create positive holes that can be filled to conduct electricity. Yes, that's the answer. Okay, boron has more valence electrons. No, that would be something like arsenic or something like that. And boron's electronegativity is high, so it pulls electrons more strongly than silicon. No, it's not that strong. You know, it's not stronger than silicon. So the answer is that it has the fewer valence electrons. Now, I did post a Veritasium video that had to talk about transistors, and I think it really helped me visualize what's going on with these little holes. Number 3, which of the following substances would be expected to have the highest melting point temperature? Okay, iodine, that's going to be a molecular solid, fairly low. Mercury, somewhere medium. Silicon dioxide, okay, that's one of our network covalent solids, definitely very, very high. Tetraphosphorus decoxide, okay, that's going to be molecular, that's going to be very low. So the very lowest ones would be D and A. Okay, B would be somewhere, higher, but certainly silicon dioxide. Just memorize your network covalent solids. Number 4, considering the compound SO2, CO2, PbO2 when listed in order of increasing strength of interparticle forces. Okay, well, SO2, we should kind of have that memorized, that it's going to look something like that, and it would have a resonance structure. So it's going to be a bent molecule. It's going to have DDI, intermolecular forces. CO2, okay, is going to be a linear molecule like that, pretty much nonpolar, so that would probably be London dispersion forces. And PbO2, that's ionic. It's a metal and an non-metal. So of these, I'd say this is going to be my lowest one. So I'm looking for CO2, and then I'm looking for SO2, and then I'd be looking for my ionic PbO2, and that's going to be answer A. So again, it comes down to relate each compound to its intermolecular forces. Number 5, the figure above shows the side of an enzyme, okay, shown in solid and dashed lines with specific amino acids bound to a nucleotide. What's the interaction that shows how the nucleotide and enzyme bind, shown at the indicated arrows? Okay, what it's really saying here is what kind of intermolecular forces is going to be happening here. And I see that I have an O and an H, and then H is bonded to another O on another molecule. That's, so we have an H bonded to an O. I think we have to say that's hydrogen bonding. Okay, that's hydrogen bonding, very polar bond. Now notice for hydrogen bonding is you have this H that is physically, covalently bonded to one atom, and it's attracted to another atom. Okay, so that is what makes this a hydrogen bond. It's kind of tethered between two very polar atoms. Okay, number 6, a typical phase diagram. So look at the phase diagram. We're supposed to remember that that's a gas, and that's a liquid, and that's a solid. At what point on the diagram do gas and liquid exist at equilibrium? So right here between the gas and the liquid lines, okay, so we're talking about point C, okay, that's where it's between gas and liquid. And what would that be? That would be something that is boiling. That's something that you have a liquid and it's got bubbles going on in here. Okay, so that's the boiling. If we had other lines where we ask about this, that would be the lines where you see freezing, and here would be the lines where sublimation's occurring. But we're talking about liquid and gas, so we're talking about boiling. Answer C. A 50 milliliter sample of an unknown liquid is placed in an evacuated closed container and allowed to reach equilibrium. Which of the following increases the vapor pressure of the liquid in the container? So we're saying we have a closed container, we have some liquid. That liquid is going to leave, become vapor. And because it's a closed container, then those vapor particles are going to turn back into liquid. So you're going to end up with a certain pressure, okay, a certain pressure, which we're going to call the vapor pressure. So which of the following increases the vapor pressure? Okay, increasing the temperature. Temperature is the only thing that will change that pressure. If you add more liquid, okay, then it's going to come to a new equilibrium with the same pressure. Transfer the liquid to a container with twice the volume. Okay, if you change the volume, it's still going to come back to that same pressure. And pump another gas in there. That might increase the total pressure, but it's not going to change the vapor pressure. So the only thing that's going to change that pressure is temperature. Now remember what's going on is we have a gas. So let's just say it's helium gas. Then we're going to have helium as a liquid. It's not a very good choice. Okay, turning into helium as a gas. So if we say, well, what's the constant going on here? Okay, the constant is going to be the partial pressure of helium gas, and that's all. So the idea is that pressure is going to be a constant, and the only thing that changes that constant is temperature. So temperature is the only thing that changes vapor pressure. Number 8, which of the following properties is expected to be lower for hydrazine than for N2O4? Okay, again, you got to think about intermolecular forces. So we have nitrogen, okay, bonded to hydrogens. And when we have nitrogen bonded to hydrogens, then we shouldn't be surprised that we're going to get hydrogen bonding. And then we have N2O4, okay, so nitrogen, and we're going to be bonded to oxygens. Okay, and what's going to happen here, that's going to be a nice nonpolar sort of molecule. So that's probably just going to be London dispersion forces, okay, because it's pretty nonpolar. But the point is that certainly the N2H4 is going to be a stronger IMF. So which of the following is expected to be lower? Well, if you have a stronger IMF, then you're going to have a high heat of vaporization, a high boiling point, high melting point, high heat of fusion. The only thing that's going to be low is vapor pressure. So large IMF, okay, goes with a small vapor pressure because it's very hard for those particles to escape. So everything goes with high IMF is large, 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 except for vapor pressure, which is low. Number 9, a 0.5 mole sample of fluorine is introduced into an evacuated container. In a two-step process, the Kelvin temperature of the sample is tripled, and then the volume is halved. Which of the following one-step changes to the original sample would result in the same final pressure as the two-step process? So we have to think about this. You have a 0.5 mole sample is introduced into an evacuated container. Okay, two steps. One is we're going to triple the temperature. So let's say the pressure, whatever pressure we have, if you triple the temperature, then that's going to triple the pressure. So now we're going to be at 3 times the pressure. And then you're going to say you're going to take the volume and cut it down to half. Well, half the volume is going to double the pressure. So this is going to change into 6 times the pressure. So what change will cause this to be 6 times the pressure? And what we're doing, we're adding moles. So if 0.5 moles causes P, then we need 6 times that. We need 3 moles. Okay, 6 times 0.5, 3 moles. So that's why we have to add 2.5 moles of F2 in order to get 6 times the pressure. So we're looking for some way to get 6 times the pressure. Okay, number 10, what's the ratio of the root mean square speed of helium to that of helium at 100 to helium of that at 50. Well, we know that 100 degrees, I'm going to add 273, that's going to be 373 Kelvin. And if I have 50 degrees, we'll add 273, we're going to get 323 Kelvin. Now we're going to go back to our first page where we see the root mean square formula. So the velocity is the square root of 3RT over molar mass. So we're going to have 3RT over the molar mass. And that's going to be the square root of that whole thing. And again, we're going to do the same thing. The difference is that this temperature up here on the top is going to be 373 Kelvin, and the one below it is going to be 323 Kelvin. And we can see what's going to happen. Everything else is going to cancel out because everything else is all the same. So we're just going to end up here with answer B, where it's going to be the square root of 373 over 323. And that's the answer. It's kind of a math problem. Number 11, equal masses of helium and neon are placed in a container. Which of the following are true? They're both at 25 degrees. Okay, the partial pressures of helium and neon are equal. Okay, the partial pressures of helium and neon are equal. If I have equal moles of helium and neon, then I would say yes, that's true, but I have equal masses. So that's not the same thing. I'm going to have a lot more helium particles than I have neon particles. So the partial pressure of helium would be greater. So one is not true. The average kinetic energy of helium and neon, yeah, that's definitely going to be true. At the same temperature, they have the same average kinetic energy. The root mean square speed of helium and neon are equal? No. Okay, the reason that they have the same kinetic energy is because the lightweight heliums are moving much faster than the heavier neons. So the only one here that's true is B. B is, 2 is the only one. B is the right answer. 2 is the only true statement. Okay, what's the molar mass of a gas at STP if it has a density of 2.86 grams per liter? Well, this one depends on, do you know the density formula? You know, it's PV equals nRT, but if you know the density version of that, and that is the molar mass is equal to dirt over P, so dRT over pressure. And we can put in our numbers here, so what do we know? Molar mass of a gas, okay, density 2.86 grams per liter. Okay, R 0.0821 liter atmospheres per mole Kelvin. And STP is 0 degrees Celsius, which is 273, so 273 Kelvin on the top, and divide by the pressure, and the pressure STP, that's 1 atmosphere. Okay, so if we do all that formula, 2.86 times 0.0821 times 273 divided by 1, we get 64. Okay, number 13. Helium is considered the most ideal of all the real gases. How come? Now, an ideal gas is one that has no volume, okay, no volume at all, and it has no intermolecular forces. So no volume, no intermolecular forces, and those are the two things we're looking at to make something an ideal gas. So why is helium very ideal? Helium has a filled electron shell. That's true. Okay, that's one of the reasons it's very non-reactive, but it has nothing to do with why it's ideal. It has very weak intermolecular forces, yes, okay, because the closest to like no intermolecular forces. And it has a very small atomic radius, yes, that's part of it because it's so tiny. Because an ideal gas has no volume and no IMFs. Helium has very small volume, very weak IMFs. So it's 2 and 3 only, answer C. Compared to pure water, salt water has a higher, boiling point, boiling temperature. Okay, so something that's important here, when we're talking about boiling temperature and things, that shows up in two places. Okay, it shows up when you're talking about pure substances, okay, comparing one pure substance to another pure substance. And if that's the case, then we're talking about intermolecular forces. But if we see that we're talking about solutions, Okay, and that's what we're doing here. We're talking about pure water, so there's no solute in there versus salt water. If you're talking about solutions, then you're talking about how many particles are in that solution. Okay, and the more particles, the higher the boiling point goes, the lower the freezing point goes. So salt water, because it has particles in there, that's going to raise the boiling point. So salt water has a higher boiling point, boiling temperature than pure water. Okay, it would have a higher boiling point, it would have a lower freezing point, and it would have a lower vapor pressure. Okay, and none of these are higher. Now, boiling point would go up. Okay, 15. Green spinach leaves are ground up and mixed with ethyl alcohol. A sample of this mixture was then placed on chromatography paper, which is placed in a test tube with a small amount of ethyl alcohol. So the ethyl alcohol is a solvent. It's going to move up the paper and take some of the pigments with it. At the same time, the pigments are going to stick to the paper a little bit, adsorb to the paper. Okay, the results of the experiment are shown 20 minutes later. Okay, which of the following might be concluded about the pigment circled that traveled 5.5 centimeters? So this guy way up here. Okay, it is less soluble in ethyl alcohol and less adsorptive. Okay, well, maybe it's less adsorptive. It means it doesn't stick to the paper. But if it wasn't soluble, it wouldn't move up very much. So that's not the answer. It's less soluble in ethyl alcohol and more adsorptive. Okay, well, then that would definitely push it down toward the bottom. That would not work. It's more soluble in ethyl alcohol and less absorptive. Okay, that's the answer. Because the more soluble, the farther it's going to go. And the less that it adsorbs, the less it sticks to the paper, the farther it's going to go. So those guys, since it goes the farthest, both of those are true. And D, it is more soluble and more adsorptive. Okay, more soluble, yes, that would get it farther along, but more absorptive would keep it back. So answer C is the best answer. Okay, now we're on to free response. Okay, a student collected a sample of hydrogen gas by the displacement of water as shown in the diagram above. The relevant data are given. Okay, so this is like when we did the Schlieren lab, so the magnesium and hydrochloric acid. Now what happens here? Calculate the number of moles of hydrogen gas that's collected. Well, we have to keep in mind that the gas inside, okay, is a combination of hydrogen gas and there's also some water vapor inside there, both of those. And we have to subtract the water vapor temperature, the water vapor pressure, which is given for that temperature, from the atmospheric pressure. So that's what this first step here is. Take the atmospheric pressure, because these two levels are the same, the water level and inside the tube, then we know the pressure inside that tube is 745, but 23.8 of that is due to the water vapor. So what's left over, the 721, that is the pressure of the hydrogen. And if it's the pressure of the hydrogen, we have to change that to atmospheres because we're going to use PV equals nRT. So we're saying PV equals nRT. We want moles, so we're going to do N equals PV over RT. Okay, we know our pressure, okay, because of the vapor pressure changed into atmospheres. We want the volume. We're going to do that in liters, so 90 milliliters change into liters. And then we have R, and we have to change our temperature to Kelvin. So once all that's done, we get a value for the moles of hydrogen. Calculate the number of molecules of water vapor in the sample of gas. Okay, well, molecules, and we want water vapor. So now water vapor, same deal. We know it's pressure. Okay, we just saw that there. It's 23.8. So that's the pressure we're going to use. Change it to atmospheres. We know the volume. We're still using PV equals nRT, looking for moles. And we have our R, and we have our temperature, so we can get our moles of water. And calculate molecules. So we take the moles. We use Avogadro's number, 6.02 times 10 to 23. And we get this answer, which is molecules of water. Calculate the ratio of the average speed of hydrogen to the average speed of water. Well, we know that hydrogens, it's a diatomic molecule, so they are going to weigh 2, more or less, 2 AMUs. And the water's H2O, we know it's going to weigh like 18 AMUs. So we're going to use our Graham's law we saw on the first page. So the velocity of hydrogen over water is equal to the molar mass of water over hydrogen. So it's the square root of 18 over 2, which comes out to be 9. So it's basically 3 to 1. So the hydrogens that are a lot smaller are traveling about 3 times faster, 2.9 times faster than the water molecules. Which of the two gases, H2 or H2O, deviates more from ideal behavior? Explain. Okay, again, how do you deviate from ideal behavior? The bigger particle size you have, that makes a difference, and the stronger the IMFs, the more that makes a difference. Well, certainly H2O is bigger than H2. It's got the oxygen. And H2O, because it's got hydrogen bonding, where hydrogen's only got London dispersion forces, then that's going to make a big difference as well. So water will definitely be the one that deviates from ideal behavior. That means, let's say you're doing a gas law problem. If you increase the pressure and pressure and pressure, the volume of hydrogen gets smaller and smaller. The volume of water is going to get smaller and smaller, but then it's actually going to turn into a liquid, and it's going to, even if it doesn't turn into a liquid, it's just not going to give you the right answers because they're going to start attracting each other the closer they get to each other. Okay, consider the graph of the following vapor pressure of diethyl ether, ethanol, and water. For the 3 liquids, rank them in terms of increasing strength of intermolecular forces. Okay, so we can take any temperature, okay, and let's just say we're going to go with, temperature right here. Okay, about 25, 30 degrees. Okay, and we can see what's happening is that the bigger the intermolecular force, the harder it is for particles to escape. So the tiny vapor pressure is going to go along with a large IMF and vice versa. So if we want to go increasing strength, we want the one with the biggest vapor pressure first, and then we'll get less and less. So I would say that diethyl ether, that's the biggest one first. Then ethanol, that'll be the second one. And then water, that'll be the third one. Water will be the strongest. Okay, I'm going to clean up my lines. But just what we do is we're going to look at the vapor pressure and relate that to IMF and the reversed. Explain how the rank can be inferred from the vapor pressure of the liquids shown in here. Okay, so it says substances with weaker intermolecular forces have higher vapor pressure. Okay, and the idea is the weaker the intermolecular force, the easier it is for the particles to escape from each other and become vapors, so the higher vapor pressure. Okay, explain how the rank can be justified using intermolecular forces. Okay, well, that's an important one. So what we're going to say now is, okay, the diethyl ether. Okay, we have to remember, what is diethyl ether? Diethyl ether is 2 carbons with an oxygen, 2 carbons, and the oxygen is going to make it bent. So it's going to be a little bit of a polar molecule. It's going to be DDI. Okay, then we're going to have ethanol. Ethanol is going to be 2 carbons and an oxygen and a hydrogen, so we're definitely going to be having some hydrogen bonding going on, okay, right here, because of this hydrogen will be ready to bond onto something else. And water molecule is going to have 2 places where these hydrogens can be attracted. So that's what it says here. The diethyl ether has only dipole-dipole interactions. That will be the weakest, IMF. The ethanol will have one site of being able to do hydrogen bonding. The water will be able to do it twice. Okay, and so it's going to be the strongest IMF of the group. So one molecule of ethanol is shown. Draw another molecule. So again, here's what you want to do. We have oxygen and hydrogen. Okay, that makes a very polar molecule. And you want to show that that hydrogen is bonded, covalently to an oxygen, but is attracted to another oxygen or a nitrogen, okay, or a fluorine. And so we're just going to have this hydrogen in between those 2 oxygens, and that's going to be the hydrogen bond. So this is what we're looking for. It's this kind of a situation where the hydrogen is sort of tethered between those 2 very electronegative atoms. Okay, 20 milliliters of liquid diethyl ether is placed in a closed container at 20 degrees. After a while, some diethyl ether remains, so it does reach equilibrium. Describe what would be observed with the volume of the liquid diethyl ether over time. Okay, so you have some in a closed container, and that liquid, some of it's going to evaporate. Okay, so this is going to get smaller and smaller, but there's still going to be some that remains. Okay, and the volume of it is going to remain unchanged eventually. Okay, sketch the pressure. Okay, well, we have to go back to our graph, and we're saying diethyl ether at what temperature? 20 degrees. So if we look at diethyl ether, that's the green one here, at 20 degrees, so let's go up here. No, at 20 degrees, here it is. So it looks like between 400 and 500 right here, okay, and that looks like maybe it's 450, 460, 470, something like that. So this is going to go up till it gets, okay, that's 100, 200, 300, 400, 500. Okay, so this line really needs to come up between the 400 and the 500. So it should be up here somewhere. Okay, a little problem with the fonts here. They kind of goofed up. Okay, so between 400 and 500, it should come up to be something like 470 millimeters of mercury torr. Okay, write the equilibrium constant expression, Kp. Okay, so here's the formula. The liquid turns into a gas. So the Kp is just going to simply be the partial pressure of the gas. Okay, he's got it written right here. Okay, and we know that that is, he's calling it 450. Okay, so that's 450 torr. Okay, now a lot of times this is given in atmospheres. In fact, it asks for use pressure in atmospheres. So we've got to change our torr in the atmospheres. So the value of this is going to be 0.592 atmospheres. Okay. Okay, a sample of liquid ethanol is placed in a 5-liter container at 30 degrees. After an hour, all of the ethanol has been evaporated. What's the greatest volume of liquid ethanol that could have been placed in a container? Okay, so we want the amount that would just completely saturate that 5 liters, okay, at 30 degrees, which we're going to change to Kelvin. So that's going to be 303 Kelvin. That if we had any more, we would have some liquid left over. Okay, the density of the liquid is 0.789. So big thing, 30 degrees ethanol. We got to go back to our chart. Okay, 30 degrees for ethanol. Here's ethanol. Here's 30 degrees. So 30 degrees for ethanol right here. Looks like 100. Okay, 100 torr. So we're doing PV equals nRT. And like we did before, we're going to say N is equal to PV over RT. Okay, the pressure we know is 100 torr. Change it to atmospheres. So that's where we get this number. Okay, it's a 5-liter container. We got that number. R is 0.0821. And temperature, we put in 303 Kelvin. And when we get all done, we're going to get a certain number of moles. So there's our moles. Okay, we want to change moles to grams because we know it's ethanol, so we can calculate how many grams per mole. And then we're going to use the density to go from grams to milliliters. So moles to grams, grams to milliliters, and we come up with a final answer, 1.54. So it's just a big math problem. And that's the whole practice test.